Hello, calculus students. Welcome to the review for our 4.3, 4.4, and 5.1 through 5.4 test tomorrow. So we're going to work through this review starting with number 1. It says consider the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared. Answer the following and provide justifications. So letter A asks us to identify the open intervals on which f is increasing or decreasing. So if you think about the function f, first of all, this is a nice smooth polynomial function, so it might look something like that. I don't know what exactly it looks like, but I just am drawing a nice smooth curve because I want you to notice that wherever we have positive tangent lines, that's where the function is increasing, and then wherever we have negative tangent lines, that would be where the function is decreasing. So in other words, f is increasing when f prime is greater than 0, and it's decreasing where f prime is less than 0. So what we're going to do is we're going to find the critical points. We want to find the points where this function has a derivative equal to 0. That's where you'd have those horizontal tangent lines. Critical points occur either where f prime is equal to 0 or undefined. But since we know that this is a polynomial function, it'd be a nice smooth curve, so f prime will be defined everywhere. So let's start by finding the critical points. So we'll take f of x and find its derivative. So f prime of x then would be 12x to the third minus 12x squared and then minus 24x. Okay, and then to find where we have those horizontal tangents where f prime is equal to 0, let's set that derivative equal to 0. Okay, and then let's solve this equation. We're going to factor. So these three terms have a common factor of 12x, so let's factor that out. And we'd have x squared minus x minus 2, and then we'll factor that trinomial. It'll factor into x minus 1, x plus 1, x minus 2, x plus 1. So our zeros then would be at, let's see, 0 and 2. Oops, I forgot a 1 over here, didn't I? Sorry. 0, 2, and negative 1. So at this point, let's make a sign chart, okay? And this is a sign chart for f prime. Let's put the zeros, and putting them in order from left to right, we'd have a negative 1, and then 1 at 0. Oops. Hold on, let me fix that. We have 1 at 0, and then we have a 0 at 2. Okay, so remember, we're going to look at this function, okay? Let's look at numbers in each interval, plug them into this function, and see whether the function is positive or negative. We don't really care what the exact value is, we just want to know its sign. So we'll start with this interval to the left of negative 1. So think of a number that's to the left of negative 1, like maybe negative 2, and plug it in here, here, and here. And so what would happen? If I plug a negative 2 in here, I'd get a negative. If I plug a negative 2 in here, I'd get a negative. If I plug a negative 2 in here, I'd get a negative. So all 3 times, I'd get a negative. So let's just make a note of that. A negative, oops, I'm going to try a negative times a negative times a negative will give us a negative result. Okay, then let's look at the interval to the right of negative 1. So think of a number that falls between 0 and negative 1, like maybe negative 1/2. So if I plug negative 1/2 in everywhere for x, I'd have negative. Negative 1/2 minus 2 would be negative. Here, negative 1/2 plus 1 would give us a positive result. So negative, negative, positive. So let's write that down. So we'd have negative, negative, positive, so that product would be positive, wouldn't it? Because you have an even number of negatives. Then continuing on to the next interval, let's pick a number between 0 and 2, like 1. Plug it in here, we'd have a positive, a negative, and a positive. So positive and a negative and a positive. If you multiply those 3 numbers together, you'd have a negative result. And then finally, let's look at the interval to the right of 2 over here. So think of a number that's bigger than 2, like maybe 3. If I put 3 in here, here, and here, we're going to get positives every single time. So that would be a positive times a positive times a positive. That product would be positive. Okay, so now we can look at this sign chart for f prime, and we can see that Remember, the f is increasing wherever f prime is positive, so f prime is increasing from -1 to 0 and also from 2 to infinity, and then decreasing from -infinity to -1 and then 0 to 2. So our justifications would look like this. We would write, let's see, we're going to say f is increasing on the intervals from -1 to 0 and from 2 to infinity. Then we need to give a reason, because that is where f prime is positive. And then we'll say f is decreasing on the intervals from -infinity to -1 and 0 to 2, because that's where f prime is less than 0. All right, so that takes care, let's put a box around that. So that takes care of part A. Okay, let's take a look then at part B. So part B says, identify where we have relative extrema, so maxes and mins. Okay, so again, if you think of this nice smooth function, where would you have maxes and mins? Well, you're going to have a max where those derivatives change from positive to negative, and you're going to have a min where those slopes of tangent lines change from negative to positive. Okay, so let's see what's happening here. At -1, f prime changes from negative to positive, negative slopes to positive slopes. So that's going to be a min. So you might just want to make a note. Let's see, let's just write min right here, because that's where a minimum is going to happen. Then right here at 0, where f changes from positive to negative, we have positive slopes changing to negative slopes, so that's going to be a max. So let's write max right here. And then where f prime changes from negative to positive again, that's where we have negative to positive. That's where we have another min. All right, so we'll write our justifications like this. Now, let's see, it does say identify the relative extrema. So I guess we should go ahead and say what those y values are. So let's write our justification like this. So this would be for letter B. Okay, letter B, we're going to say f has a relative min of, now, what would that, and we're talking about the first relative min that happens here at -1. So if we want to actually know what that minimum is, we'd have to evaluate the function at -1. Well, I'm not terribly interested in what that actual value is, so I'm just going to call it f of -1. So we have a relative min of f of -1 at x equals -1. And we also have a relative min of, let's see, and a second one of f of 2 at x equals 2. All right, and then for the maximums, we'll say f has, well, there was just that one max, f has a relative max of whatever, that max would be whatever the function value is, f of 0. That is probably one we could figure out pretty quick. Let's see, f of 0 at x equals 0. Oh, oops, I forgot to give my justification on part 1. I apologize. Let me go back. We didn't finish. I told you that where the mins happen, but we need to give a justification. Why do we have mins there? Because what does f prime do? Changes from negative to positive, and here, negative to positive. So let's finish that. Sorry about that. So we have f has a relative min at x equals -1 and x equals -2, because f prime changes from, let's see, mins, negative to positive, all right? And then we'll say f has a relative max of f of 0 at x equals 0. At x equals 0, because f prime changes from, let's see, positive to negative. From positive to negative. All right, so that takes care of number 1. Question number 2 says, consider the function f of x equals 2x to the 4th minus 4x cubed plus 5 Answer the following and provide justifications. Okay, let's first of all identify points of inflection of f. So points of inflection are those points where there's a change in concavity. So change in concavity. Now, if we were looking at a graph of f prime, we'd be looking at where f prime changes from increasing to decreasing or vice versa, but we don't have the luxury of looking at a graph of f prime, so perhaps we'll want to use the second derivative. So if we're looking at the second derivative, we want to know where f double prime changes sign. Oops, changes sign. Okay, so let's go ahead and find the second derivative. So the first derivative, f prime of x, would be, let's see, 8x to the third minus 12x squared. All right, and then our second derivative, f double prime of x, would be 24x squared minus 24x. So now let's make a sign chart for f double prime, and that way we can tell where f double prime changes sign. So I'm going to take that second derivative and set it equal to 0. And then let's factor and find the zeros of the second derivative. So I'm going to factor a 24x out, and that's going to leave, whoopsie, let me fix that, 24x. And that's going to leave me with x minus 1. All right, so that means we have a 0 at x equals 0 and at x equals 1. So making a sign chart for f double prime, let's put those critical points on there, 0 and 1. Let's see what the sign of f double prime is in all of those intervals. So we'll start with this interval to the left of 0. So think of a number that's to the left of 0, like -1. If I were to put it in here and here, I'd have, let's see, a negative times -1 minus 2 would be negative. So we'd have a negative times a negative. Okay, so there's a negative times a negative. So that means that product is positive. All right, and then in the interval between 0 and 1, think of a number like positive 1/2. If I put positive 1/2 in for x, my first factor is positive, and 1/2 minus -1 would be negative, so that's a positive times a negative. So positive times a negative, that means that product is negative. And then let's go to the right of positive 1. So think of a number like positive 2, plug it in. We'd have a positive times a positive, positive times a positive. So that means my product is positive. Okay, so we can see a change of sign right here at 0. F double prime changes from positive to negative, and then at positive 1, F double prime changes from negative to positive. So those would both be points of inflection. So we're going to say, and then this is our answer justification for letter A, we're going to say that our function f has points of inflection, you can just say POI for that, at x equals 0 and at x equals 2. And our reason is because that's where f double prime changes sign. We don't need to talk about whether it's positive to negative or negative to positive. We're not identifying extremum here. We are just talking about f prime changing sign. So that's letter A. Let's draw a box around that. And then letter B says, let's see, letter B says, determine the intervals on which f is concave up or concave down. So you'll remember f is concave up where f double prime is positive and concave down where f double prime is negative. So back to our sign chart, we can see that to the left of 0 and to the right of 1, f double prime is positive, and then in between 0 and 1, f double prime is negative. So our justification then will look like this. Oops, how did I do that? Let's see. That's what I wanted to do. Okay, so letter B looks like this. We're going to say f is concave up, and it doesn't matter whether you mention up or down first. I'm just going to say up. Where is it up? It's concave up wherever f double prime is positive, so from negative infinity to 0 and 1 to positive infinity. So we're going to say f is concave up on the intervals from negative infinity to 0 and from 1 to positive infinity because f double prime is positive there. And then we'll say f is concave down on the interval from 0 to 2 because that's where f double prime is negative. Now, looking back over my work here, I realized I made a couple of mistakes. You probably noticed that. I don't know what I was thinking. I don't know why I said 2 here. That's supposed to be 1. And then I did it again right here. So that's supposed to be 1. So sorry about that. And sorry about that confusion. Okay, question number 3 is asking us to review the second derivative test because it says the continuous function f has critical points at x equals -1, x equals 0, and x equals 2. The second derivative is f double prime of x equals 2x to the third plus 5x. What conclusions, if any, can be made about the relative extrema of f? So the second derivative test, let's just review that real quick. This is the second derivative test, and this is a test for relative extrema of f, all right? And here's what the test says. It says, first of all, if we have a c where f prime of c is equal to 0, okay, the first derivative is equal to 0, and if the second derivative exists, which it does in this case, then we'll look at f double prime of c. If f double prime of c is greater than 0, then we have a relative max at that c. If f double prime of c is less than 0, we have a relative min. And then remember f double prime of c, if it's equal to 0, unfortunately, that's where the second derivative test fails. So we will have no information about a relative extrema at that point. If we knew what f was and could find f prime, we could go back to the first derivative test and see if f prime changes sign. So let's just talk about this kind of narrow situation where we know the second derivative and we know that there are critical points. Now, we know that those critical points would be where f prime of that particular c is equal to 0 because this second derivative is a polynomial function, so that means the first derivative was a polynomial function. If you go all the way back to f, it was a nice smooth curve, so that means that these are x values where f prime would be equal to 0. So what we're going to do if f double prime of x is equal to 10x to the third plus 5x. Let's evaluate f double prime of x at each of those critical points. So at -1, we'd have 10 times x to the -1 cubed plus 5 times -1. Now, am I really interested in what that number actually is? No, not really. I just need to know if it's positive or negative. So this is going to be negative because we have a negative plus another negative. So I know that this is going to be a negative number, okay? F double prime of, let's see, what's the next one? 0 would give us 10 times 0 cubed plus 5 times 0. That's equal to 0. And then f double prime of 2 would be 10 times 2 cubed plus 5 times 2. I know that that's going to be a positive number. All right, so here's the conclusion that we'll make. We'll just have to say, we can say that f has a relative min. F has a relative min at x equals -1 because f double prime was, well, I guess I should say of -1. So let me erase that. Let's say f double prime of -1 is less than 0, all right? And then we'll say f has a relative max at x equals 2 because f double prime of 2 was greater than 0. And then we'll just have to say let's just say the second derivative test fails at x equals 0. So we can make no conclusion about extremum at that point. Okay, before we do number 4, I just want to encourage you to take a look at that website that I posted in Google Classroom, because you can practice a bunch of these problems and get really good at it. So we're going to look at these graphs and identify which one is f prime, and f double prime. So it is okay just to go with trial and error, okay? So I'm just going to try, have a feeling that this graph C is f, all right? So I'm going to highlight it. Let's see. Let's highlight it in yellow. So I think that this is f. And now, as I look at it real quickly, well, what I would look for next is I would look for f prime. If this is indeed f, and it might not be. If it's not, we'll try something else. But I'm going to look at those extrema, because that's where we would have horizontal tangents, right? Okay. So wherever there's a horizontal tangent, f prime will cross the x-axis. Well, if you look here, let's see, look at this graph. Let's see, where we have this extreme, I have a 0 right there. Let's switch to a pen. Also, where we have this extrema, horizontal tangent, look, that same graph crosses the x-axis right here. Here's another extreme, that's a relative min, and the graph crosses the x-axis. So I am predicting that, I don't think I'm predicting, I think I'm feeling pretty confident that, let me see, I'm trying to get another color here, that, let's see, which one was it, that this is, graph B is f prime. And so I use zeros of f prime to test against f. So if I see a max or min, I look for zeros to test which one is f prime. And then for f double prime, I look for concavity. So for example, from here to here, okay, my graph that I think is f is concave down, okay? So if you look at this black graph, notice it's always below the x-axis. It's negative. Remember, a graph is concave down when the second derivative is negative. And then here, where what I think is f is concave up, notice that this black graph is above the x-axis. And then here, where f is concave up, it's above the x-axis. So I think I'm feeling pretty confident, very confident that we're right. So we think that C is f. Let me change that. We think that C is f. We think that graph B was f prime and graph A was f double prime. And then again, I encourage you to go take a look at that worksheet, and I mean not worksheet, but that website that I posted in Google Classroom, and you can practice a whole bunch of these. Okay, so you'll have a question like this on the test where you'll be looking at the graph of f prime. So don't let your brain get tricked. F prime, write it all over the place so you know you're looking at the graph of f prime. And then what we're going to do is talk about the behavior of f as we look at the graph of f prime. The part A asks us on which intervals is f increasing. So if we're looking at the graph of f prime, we know that f is increasing wherever we have positive tangent lines. In other words, wherever f prime is greater than 0. Okay, so looking at our function, we can see that from here to here, f prime is greater than 0. And then from here all the way to there, we're going to have to break it up there, because at that point we have f prime is equal to 0. We have a horizontal tangent. So that means that our function, well, let me just draw it real quick. If I have a horizontal tangent, at that point the function is neither increasing nor decreasing. So we'll have to break up the intervals and then pick it up again to the right of that horizontal tangent where f prime is positive again. So for letter A, let's write our justification like this. Let's say that f is increasing wherever f prime is above the x-axis. So that would be from -1 to 3, and also it's above the x-axis from, now right here, this we pick it up right here, somewhere between 4 and 5. We could do the algebra and figure it out. We could find the graph of this line and set it equal, or the equation for the equation for this line, set it equal to 0, and we can find this to be exactly 4 1/4. So we're going to pick it up again at 4 1/4. So let's see, 4 1/4, all the way to 6, because that's where we have that horizontal tangent, and then to the right of 6 to 7. So that's where f prime is above the x-axis. So wherever f prime is above the x-axis, we know f is increasing there. All right, then letter B says, for which x values does f have points of inflection? So we have points of inflection where f prime changes from increasing to decreasing or decreasing to increasing. Let me just real quick draw a point of inflection. Okay, like here. Here we have slopes that are decreasing, and then they change to increasing slopes. And we're talking about tangent lines there. So we want to look for wherever f prime changes from increasing to decreasing or vice versa. So in other words, we're looking for extrema of the f prime graph. So we have an extremum. Let's just kind of highlight. We have one here. We have an extremum here. We have one here, and we have one there. So it looks like there are 4 times where there's a change in concavity. So we're going to say in letter B, f has a point of inflection at all those extrema, at x equals 1, at x equals 4, at x equals 5, and at x equals 6, because that is where f prime changes from positive to negative, or vice versa. On the quiz, a bunch of you said and vice versa. You know, that doesn't make sense. It's either positive to negative or negative to positive. So if you don't want to say vice versa, you can just say or negative to positive. All right, and then letter C says, identify the intervals where f is concave up. Well, we're looking at the graph of f prime, so we need to justify our answer in terms of f prime. So a function would be concave up. Let me just sketch a little concave up curve. Okay, it's concave up wherever those tangent lines are increasing. Here we have negatives that are getting closer to 0, and then they get more and more positive. If we have a graph that's concave down, then you can look at those tangent lines that are decreasing. So it's concave up. Oh, well, we don't care about that. For this one, we care about where it's concave up. So identify the intervals where f is concave up. So that would be wherever the graph of f prime is increasing. So it looks like it's increasing from -1 to 1, okay? Then we have a big old decrease, and then increasing from 4 to 5, and then a decrease, and then increasing from 6 to 7. So we're going to say that f is concave up on the interval from -1 to 1, and from 4 to 5, and from 6 to 7, and our reason is because that is where f prime is increasing. All right, and then finally letter D says, identify the relative extrema of f. So we have relative extrema of f wherever we have those tangent lines that change either from positive to negative or negative to positive. Like if this were f that we're looking at, here we have those tangent lines that are positive and then they change to negative, or here negative and then they change to positive. All right, so in other words, we want to look at, as we're looking at the graph of f prime, we want to look for zeros. So we have a 0 and we have zeros. Let's see, we have zeros at 3, at whatever this is, I think it's 4 1/4. Now there's a 0 here, okay, but notice that f prime is positive to the left of that 0 and positive to the right of that 0. So that's not a relative min or max, that's just a change in in concavity because f prime changed from decreasing to increasing. But it's not a max. So we only have one relative max, and the relative max would be where f prime changes from positive to negative. So that would be here. Oops, I meant to say we have a max right here because here f prime is positive and then it changes to negative. And then this is a relative min because f prime changes from negative to positive. All right, so we'll write our justification like this. We will say the graph of f has a relative, and it doesn't matter which one you mention first. So I'm going to mention the max first. A relative max at x equals 3 because f prime changes from positive to negative. All right. And then for our other, oops, that's weird. Okay, sorry this is going to get a little messy, but for some reason it won't all scroll up. So I'm just going to, I need a little more space though. So I'm going to slide this up so I can write the rest of part D. So for the rest of part D, we will say that f has a relative min at x equals, I think that, or I know it's 4.25 because f prime changes from negative to positive. Okay, and if you were paying close attention, you may have noticed that on part A, I forgot to write the reason. So let's go back and add that real quick. Remember, part A was asking where is f increasing? F is increasing wherever f prime is greater than 0. So we already said that f is increasing on these intervals, -1 to 3, and -1 to 3, and 4 1/4 to 6, and 6 to 7. And we just need to add because f prime is greater than 0. So now let's start the integration part of our review. So in number 6, we're going to be finding some indefinite integrals. So remember, when you find an indefinite integral, you're looking for a family of functions, all of which have the same derivative, which would be the integrand. So in number 1, we might want to start by rewriting that integrand. Let's rewrite it as the integral from, well, I almost wanted to say bounds, but remember this is an indefinite integral. So I'm going to rewrite that 1 over x to the 4th as x to the -4th, and then minus 3x squared dx. Okay, and then as I work this, I'm going to write more than you probably would write. This is work that you do in your head, but I just want to make sure that you can follow along what's happening. So to find the antiderivative of the first term, that would be x to the -4 plus 1 over -4 plus 1, and then minus 3x to the 2 plus 1 over all over 2 plus 1, and then don't forget your plus c. And then simplifying a little bit, we'd have x to the -3rd over -3, and then minus, let's see, this would be 3x cubed over 3 plus c. And then just simplifying a little bit more, I'm going to rewrite this without the negative exponent, this first term, and then we can cancel the 3's here. So we would end up with, let's see, -1 over 3x to the +3rd, and then minus, these 3's will cancel, x to the 3rd plus c. And then again, you could certainly go from here to here. You don't need to write all that work, but I just want to make sure you could follow along. So there's letter A. Now letter B, let's see, we need to find the derivative of cosine. So you might remember, this is a little mnemonic device to help you remember to derive and integrate sine and cosine. So if you write s, c, -s, -c, and just remember when you go this way, that's when those are derivatives. And then go from bottom to top when you integrate. Okay, so if we're finding the integral of cosine go up, then it's going to be positive sine. So that first term of the antiderivative then would be sine x. And then the next term, you might be tempted to you might be tempted to rewrite this as, and don't write this down, just watch what I do. Rewrite this as 2x to the negative first. And then when you use the power rule, that would be 2x to the negative 1 plus 1 all over negative 1 plus 1. So there's the problem we ran into. We'd have the 0 in the denominator. So what you need to remember, let me erase that because that's not what we want to do. Oops, that's not the eraser. Try that again. What we need to remember is that the integral, let me write it up here, the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So that's what we want to use here. So when we integrate 2 over x, that would be 2 times the natural log of the absolute value of x. So this would be plus 2 ln of the natural value of the absolute value of x, and then plus c. All right, so there's letter B. And then I'm kind of running out of room, so I think I'll do letter C down here. So I'm going to rewrite this as I'm going to distribute, okay? And remember that square root of x is the same, let me write it here. Square root of x is the same thing as x to the 1/2. So when I distribute, when I take x to the 1/2 times x, that would be x to the 3/2, and then minus x to the 1/2 dx, all right? So now when we find the antiderivative, that would be x to the, again, I'm going to write more than you really need to, x to the 3/2 plus 1 over 3/2 plus 1, and then minus x to the 1/2 plus 1 over 1/2 plus 1, and don't forget the plus c. And then simplifying a little bit, 3/2 plus 1 is 5/2. And then dividing, when we divide by 5/2, that would be the same thing as multiplying by 2/5. So I'm going to rewrite this as 2/5 x to the 5/2, and then minus, let's see, 1/2 plus 1 is 3/2, and then dividing by 3/2 is the same thing as multiplying by 2/3. So that would be 2/3 x to the 3/2, and then plus c. Okay, for number 7, I just want to remind you that the names of these functions that we've used, s and a and v, are common names for position, velocity, and acceleration. So let me just write this down just to remind you that s of t is often the name of a position function, and then if we want velocity, we need to take the derivative of s of t. So that would be, the velocity then is s prime of t, which would be our velocity function, and then acceleration, which is the first derivative of velocity and the second derivative of position, that is acceleration. Okay, so to solve this differential equation in number 7, what we're looking for is we're trying to find s of t. Okay, so if we're given a of t, that means we're going to have to integrate twice. We're going to integrate the first time to get velocity, and then we'll integrate velocity to get position. So let's start by taking the integral of a of t, which is 6t dt. Okay, that's going to be equal to 6t to the second over 2, which reduces to 3t squared plus c. Now, remember we just integrated, this is acceleration, we just integrated it and we got velocity. We're given, remember, that v of 0 is equal to -2. So when t is 0, the output of that function is -2, so we can plug that in and find c. So we're going to rewrite this as 0 equals 3t squared. Oh, sorry, not t. We have a value for t. When the output is 0, the input is, oh, I'm sorry, I've got that backwards. Let me look at this again. The input is 0 and the output is -2. So let me write it the right way. So -2 is equal to 3 times 0 squared plus c. So that means c is equal to negative 2. So our velocity function, v of t, is 3t squared minus 2. So now, let's integrate that to get our position function. So the integral of 3t squared minus 2 dt would be 3t to the third over 3, so that reduces to t cubed, and then minus 2t, and then don't forget your plus c. Now, we're given that s of 1 is equal to 7, so when t equals 1, the output is 7. So we can use that then to find our constant. So 7 is equal to 1 cubed minus 2 times 1 plus c. So 7 is equal to 1 minus 2 plus c, or negative 1 plus c, so c is equal to 8. All right, so now we can write our final answer then. And our final answer for s of t would be s of t is equal to t cubed minus 2t plus 8. Okay, then for number 8, we're going to rewrite this integral as the limit of a sum. So let me just remind you what the formula was. We're going to take the limit as n approaches infinity of the sum as k goes from 1 to n of f of a plus k times delta x, and then times delta x. So you'll recall that is a sum of an infinite number of rectangles whose width is delta x and whose height was f of a plus k times delta x. Okay, so let's identify some parts from this integral. We know from the integral that a, the lower bound, a would be 3. Okay, so let's write that down. So we know that a is equal to 3. And then let's also figure out what delta x is. Remember, delta x is b minus a over n. The upper bound minus the lower bound over n. So that would be 9 minus 3 over n, or 6 over n. Okay, so now let's go ahead and write our limit and plug stuff in. So we'd have the limit as n approaches infinity of the sum as k goes from 1 to n. Now we've identified that a, remember, was 3, okay, and delta x is 6 over n. So let's plug that in. Then we'd have f of 3 plus k times 6 over n, and then times 6 over n. So now what we're going to do is we're going to take this, we're going to evaluate this function, okay? So we're going to take our x, our input, which is 3 plus k times, actually we could call it 6k over n, and we're going to put that in right here, okay? When you evaluate a function, you just put the input in where x should be. So this would be equal to the limit as n approaches infinity of the sum as k goes from 1 to n of, now, if f of x is 2x cubed, then f of 3 plus 6k over n would be 2 times, parentheses, 3 plus 6k over n cubed. It would look like this. 2 times, parentheses, now we're going to take all that and put it in for x, so it would be 3 plus 6k over n. All right, and then times, cubed, remember we cubed that, and then 6 over n. Okay, so again, all we did is we took this input, all right, put it in for x. So 2 times all that input to the third power. And that's it. And then number 9 is a little bit easier. It's easier to take the limit of a sum and rewrite it as an integral. So let's go ahead and start our integral. Now, lower bound. Lower bound is going to be a. And where we're going to find a is right here. So we know our lower bound is a. Okay. We also know that b minus a over n equals delta x. And delta x you'll find right here. Delta x is 3 over n. Okay, so we know that our lower limit of integration is 2, so I can rewrite b minus 2 over n equals 3 over n. So therefore, b must be 5, because 5 minus 2 equals 3. So we go from 2 to 5 of, now, what is our function? Okay, well, if all of this is your input, okay, we're just going to take all of that and replace it with x. So it just turns out to be the integral from 2 to 5 of 1 over x, oops, I changed my color, I didn't mean to do that, 1 over x dx. And that's all there is to it. All right, so just look at the function and find what x is. All of this stuff is going to be replaced with x, and what's happening to your input? Well, we're taking 1 and dividing it by the input, and that's all we need to do. Okay, so in number 10, we are now going to use data in a table to find some approximations. We're going to use Riemann sums to approximate. So this first one, letter A, says use a left Riemann sum and 3, let me underline that, 3 subintervals to approximate the integral from 2 to 14 of f of t dt. So we're going to start by saying the integral from 2 to 14 of f of t dt is approximately equal to, remember this is going to be the sum of the areas of a bunch of rectangles, so it's going to be approximation for the integral. Now if we're using 3 subintervals, we're going to have to break this up into 1 interval, 2 interval, and 3 intervals. We're using a left Riemann sum, so that means we're going to use, in each interval, we're going to use the leftmost x value in each of those intervals for our height, okay? And then our delta x is going to be the difference from one x value to another, all right? So our first rectangle has a delta x of from 2 to 6 is 4. So we're going to take 4 times that leftmost function value, which is 4, okay, plus our next rectangle has a delta x of 4 again. Oops. Delta x of 4 again, and we'll take that width and multiply it by this leftmost height. So it's going to be 4 times 15. And then our last rectangle, again, there's a delta x of 4 that we will multiply the height of the leftmost function value, 4 times 8. And that's it. There's no need to do any more arithmetic. You can leave your answer just like that. So then in letter B, this time let's use a right Riemann sum with 6 subintervals to approximate our integral. So I'm going to erase all this stuff. Okay, this time we have 6 subintervals. So that would be 1, 2, 3, 4, 5, 6. Now, for each of those, delta x is constant in this example. Each time delta x, oops, I meant to say equals, delta x is equal to 2. Okay, so delta x equals 2 in every one of these subintervals, so I'm not going to write it every time. So let's get an approximation. We'll take the integral from 2 to 14 of f of t dt is approximately equal to, our first rectangle has a width of 2 and then a height. To get the height, we're going to take, in this case, the rightmost y function value in each rectangle. So in our first rectangle, it has a height of 2, a width of 2, and then a height of 9. Plus, in the second interval, okay, we have, again, a width of 2, and then in this interval, you want the rightmost function value, so that would be 15. So we'll take, 2 times 15, plus the next rectangle has a width of 2, and the rightmost function value is 6. And then we'll just continue on down the line. So it'd be 2 times 6, and then 2 times 8, plus 2 times 5, plus 2 times 10. And that's our right Riemann sum. Okay, and then part C asks us to use a midpoint Riemann sum with 3 subintervals to approximate the integral. So let's break this up into the 3 subintervals again. 1, 2, 3. Okay. Now, delta x every time is going to be 4. Okay. For each of our rectangles, the width of our rectangle is the change in x. It's constant, it's 4. And then for our height, we're going to use these midpoint values in each interval. So we'll say the integral from 2 to 14 of f of t dt is approximately equal to 4 times 9 plus 4 times 6 plus 4 times 5. And that's it. Okay, for letter D, it says use a trapezoidal sum with 6 subintervals to approximate our integral. So this time we're using 6 intervals. So let me erase this. And we've got 1, 2, 3, 4, 5, 6 intervals. And this time, since we're using trapezoids, let's review the formula for a trapezoid. 1 half the height times the sum of the bases. Okay, so the height will be our delta x each time, and then these bases, these are going to be function values. Okay, so they'll be the y values or the output values on your table. So we're going to write the formula or the area of 6 trapezoids. So to approximate the integral from 2 to 14 of f of t dt, our first trapezoid would be 1 half delta x, remember, is 2, so 1 half the height times the sum of the bases. So the bases are our function values, 4 plus 9. That's our first trapezoid. So the second one would be 1 half the height times the sum of the bases, that's 9 plus 15, and then plus 1 half the height. So we've done our first trapezoid, our second trapezoid, now we're on to the third one, so 1 half the height times the sum of these two bases. So it would be 15 plus 6, and then plus 1 half our height times the sum of the bases would be 6 plus 8, and then 2 more trapezoids plus 1 half the height times 8 plus 5, and then our last trapezoid is 1 half the height times 5 plus 10. And again, you do not need to do the arithmetic. You can leave your answer just like that. Problem number 11 says, the amount of hot water measured in gallons in a hot water tank at time 0 less than or equal to t less than or equal to 20 is given by the differentiable function w of t, where t is measured in minutes, and then selected values of WT are given below. Part A asks us to use a midpoint Riemann sum with 3 subintervals to estimate the average value of W from 0 to t. So you might recall from class, to find the average value, if we have an integral from a to b of f of x dx, and we want to find the average value, we just need to take that integral and multiply it by 1 over b minus a. So for letter A, to find the average value of the integral from 0 to 20 of wt dt, we're going to take 1 over 20 minus 0 times the integral from 0 to 20 of wt dt, and then that we're going to approximate that with a midpoint Riemann sum. So that would be 1/20 of, now let's find that midpoint, midpoint Riemann sum with 3 subintervals. So we're going to break this chart up into 3 subintervals. So we'll go from 0 to 8, and 8 to 15, and 15 to 20. All right, so you'll notice this time delta x is not constant. Our first delta x, which would be the width of that first rectangle, is 8, okay? The second delta x, 8 to 15, that would be 7, and our third delta x is 5, all right? So, and then this is a midpoint Riemann sum, so in each of those rectangles, we want to use the middle y value for our height of the rectangle. And so we're going to take 1/20 of, we'll first take 8 times the middle y value, which is 10, plus the next rectangle has a width of 7 and a height of 5, and then plus the last rectangle has a width of 5 and a height of 11. Okay, so that is an estimate of the average value. And then letter B asks us, it says, using correct units, explain the meaning of this 1/20th from 0 to 20 of WTDT in context of this problem. So whenever you're asked to explain a meaning, remember, don't forget woo-woo. Okay, that stands for what we're being asked to find with units, and then when with units. All right, so let's start with the what. Okay, what does this represent? Well, first of all, if it's asking us what does this expression represent, that's what I would start with. Let's say 1/20th, whoops, I'm going to write in black, 1/20th of the integral from 0 to 20 of WT dt, okay, represents, now what was WT, or W remember, was a function that tells us how much water is in the tank at any time t. So this 1/20th of that integral would represent the average amount of, remember the watt is an amount of water, right? So average amount of water in the tank, and don't forget units. So we've said watt, now let's say what units. It's measured in gallons. And then the second W is for when, so we'll say from t equals 0 to t equals 20. So that was the when, and then let's include those units, and that would be in minutes. Problem number 12 asks us, which of the following could be the graph of y equals f of x if a left Riemann sum is an overestimate of the integral from 0 to 5 of f of x dx, and a trapezoidal sum underestimates the integral from 0 to 5 of f of x dx. So let's just do a quick analysis here. Now, if you can memorize all this stuff, it's great, but you can always sketch a quick picture to determine when a left Riemann sum is an overestimate or an underestimate. So remember, if it's a left or a right sum, what we care about is if the function is increasing or decreasing. So I'm just going to draw an increasing function and then a decreasing function. And concavity doesn't matter for left Riemann and right Riemann sums. So this is for a left Riemann sum. And so I'm going to draw a left rectangle. So I'm going to pick a point on my function. And then that should be, if this is a left Riemann sum, that's the upper left-hand corner of a rectangle. So the rectangle might look something like that, okay? If it's a decreasing function, again, just pick a point on the function, and then that point should be the leftmost corner of a rectangle, okay? So you can see here that if the function is increasing, this first one, in this increasing function, the left Riemann sum would be an underestimate, okay? And when the function is decreasing, we can see that that left Riemann sum is an overestimate. So what was this problem asking us for? It said the left Riemann sum is an overestimate. So we're looking for a function that, an overestimate. So we're looking for a function that's decreasing, okay? And then also we're told we're looking for a function where the trapezoidal sum is an underestimate. Now remember, for trapezoidal sums, what we care about is concavity. So doesn't matter whether it's increasing or decreasing. So I'm just going to draw one concave up function and one concave down function. And then I'm going to draw a couple trapezoids and see which one is an overestimate and an underestimate. So to draw a trapezoid, just pick two function points, okay? Draw a straight segment between them and draw a trapezoid. We'll do the same thing here. This almost looks like a rectangle. Let me make a function that's not quite so symmetric. So it really does look like a trapezoid. All right, so I'm going to pick a couple of function values, draw a straight line segment to connect them, and then make the trapezoid. So we can see that if the function is concave up, the area of the trapezoid would be an overestimate, and if the function is concave down, we can see the area of the trapezoid is an underestimate. Now, this problem was looking for one where the trapezoidal sum was an underestimate, so that means we want to look for a function that's concave down. So we're looking for a function that is both decreasing and concave down. So A is decreasing, but it's concave up, so it's not A. B is increasing, so we need a decreasing function. C is increasing, so it looks like it's going to be D. When you look at D, it is both decreasing and it's concave down. So that is our answer choice. Okay, number 13 says, find the area of the region bounded by the graph of y equals secant squared x, the x-axis, and the vertical lines x equals -1/4 and x equals +1/4. So let's take all those words and just write that in terms of an integral. So that would be the integral from -π4 to +π4 of secant squared x dx. All right, so let's evaluate that definite integral. So the antiderivative of secant squared x is tangent x, and that is one you need to memorize. And that is the antiderivative of secant squared x. We need to evaluate that at the bounds and then subtract that. So we'll start by taking evaluating tangent x at π4, and then we will subtract tangent at -π4. All right, so if you recall, let me draw a unit circle here. At π4, okay, tangent, that's where your x and y values are the same. And remember, tangent is y over x, so the tangent of π4 is +1. And then at -π4, let's see, that would be here, okay? And remember, all students take calculus. So we're in quadrant 4, where only cosine is positive. So this is going to be a negative function value. Tangent of π4, so the reference angle is π4, and tangent of π4 again is 1. But this is going to be -1, so it's minus -1. So our final answer is 2. Problem number 17 asks us to evaluate each of the following given these definite integrals. So this is just asking us to review our properties of integrals. So letter A, first of all, this first integral, we have the integral from 2 to 5 of 7 times a function. Remember, whenever you have a constant, you can always pull that constant out in front of the integral. So we could rewrite this as 7 times the integral from 2 to 5 of h of x dx. And then we're going to add that to the integral from 2 to 5 of f of x dx. Remember, the sum of two integrals is the same as the integral of the sums. So let's find each value. Remember, a definite integral gives you a value, and we're told that the integral from, oops, I made a mistake there. That should have been a 5. Sorry about that. Let me fix that. That should be a 5. Okay, and we're given that the integral from 2 to 5 of h of x dx is, here it is, integral of 2 to 5 of h of x dx is 2. So that would be 7 times 2 plus the integral from 2 to 5 of f of x dx, we're told, is 14. So that's plus 14. So we have 14 plus 14 is 28 for our final answer. Okay, in letter B, notice this time we have the bounds are backwards. Instead of going from 5 to 9, it goes from 9 to 5. So remember, to fix that, we can just rewrite B, letter B as the integral, the opposite of the integral. The opposite of the integral, turn those bounds around, of 5 to 9 of f of x dx. All right, and we're told that the integral from 5 to 9 of f of x dx is 8. So letter B is equal to -8. All right, and then letter C, let's say I'm kind of running out of room, so I'll do letter C down here. Okay, letter C, the integral from 2 to 9 of f of x dx. Well, look at what we're given. We're told the integral from 2, we're given the integral of 2 to 5 of f of x dx, and then the integral from 5 to 9 of f of x dx. So we can break this up into the integral from 2 to 5 of f of x dx plus the integral from, oops, that be a plus sign, plus the integral from 5 to 9 of f of x dx. So that will give us, let's see, the integral from 2 to 5 of f of x dx is 14. The integral from 5 to 9 of f of x dx is 8. And then 14 plus 8 is 22. And then last but not least, letter D. Notice that the bounds start at 5 and end at 5. So it doesn't really matter what this function is. If the bounds go from 5 to 5, that means we're talking about a rectangle that has, or an area that has no width. So anytime the bounds are the same like that, the integral is equal to 0. So that is just letter D is equal to 0. Okay, number 15, last but not least, we are going to use some geometry to evaluate integrals. So I'll draw a sketch of what this integral represents and then use a formula, formula from geometry to evaluate the integral. So letter A, I'm going to draw a sketch. Now on the test tomorrow, I will provide some graph paper like this, so it'll make these easier to sketch. So the integral from 1 to 3 of 2x dx. So this function 2x, it's a linear function. It's a line that has a slope of 2 and a y-intercept of 0. So it might look something like this, and we need to evaluate it from 1 to 3. So y-intercept of 0 and then a slope of 2. Okay, so the line looks something like this. And then we want to evaluate it from 1 to 3. Okay, so let me give it a left bound and a right bound. All right, so we just need the area of, well, this is a trapezoid, isn't it? Okay, how do you find the area of a trapezoid? It's 1/2 the height times the sum of the bases. Okay, the height, remember, is the distance from one parallel base to another. So that means the height of this trapezoid, the distance from one base to another, is 2. So this is going to be 1/2 times 2 times the sum of the bases. Well, the first base has a length of 2. So we'll put 2, and then the second base has a length of 1, 2, 3, 4, 5, 6, or we can always just evaluate our function at 3. 2 times 3 is 6. All right, and then just do the arithmetic. That's 1 times 8, which is 8 square units. Now, I used a trapezoid, but you could have done it different ways. If you want, you could break the region up into a square and a triangle. So you could have found the area of the triangle and then added the area of the square. You could do it any way you want. But letter A was B. Letter A was 8. Okay, and then letter B, okay. So this function, this is the absolute value function. That's some transformations have happened. First of all, this negative is going to flip it upside down. Minus 3 from x means it's been shifted 3 to the right, and then adding 2 will shift it up 2 units. So let me just start. I'm going to just start by sketching. Let's see, it's going to be shifted left, right, and up. Okay, I'm going to start by sketching the parent function. So the parent function would look something like this. Okay, so there's your absolute value function. Now, the negative out in front flips it upside down. So I'm going to flip it upside down. Oops. Flip it upside down. Okay, and then we need to take this upside down function. We need to shift it 3 units to the right and then up 2. So it might be easiest just to do that point by point. So let's grab a few points. Let's grab this point, and this point. Shift them 3 to the right and up 2. So 1, 2, 3, and up 1, 2. And then this point, 1, 2, 3, up 2, and shift the other one to the right, 1, 2, 3, up 2. Okay, so that is what our function looks like. All right, now we want the integral from 1 to 5. So 1, 2, 3, 4, 5. So that means we're looking at this region right here. Well, that's simply a triangle. we can find the area of the triangle by taking 1/2 its base times its height. So that would be 1/2 of 5 times a height of 2. So half of 10 is 5. All right. And then last but not least, letter C, we want the area, the integral from -4 to +6 of this function. Remember, this is the graph of f this time, of f of x dx. So I'm going to draw the areas under the x-axis. I'm going to shade those in red. Okay. And then the areas above the x-axis, I'm going to shade those in green. Okay, so now, any area that is above the x-axis, of course, would have a positive value. And then these regions that are below the x-axis, those have, it would be the opposite of the area. Remember, technically, area is defined as a positive number. So if we're talking about a region below the x-axis, it's the opposite of an area above the x-axis, so these should be negative. So let's just use our knowledge of geometry to find these areas. This first one is a triangle. It has a base of 1, 2, 3 and a height of 1, 2, 3. So 3 times 3 is 9, and then we'll take half of that. So this region would be -4.5. This region above the x-axis, this is a semicircle. Okay, we find the area of a whole circle by taking pi times its radius squared. It has a radius of 1, but we only want half of that. So pi times 1 squared divided by 2 is just pi over 2. Okay, this region is a, oops, I meant to use the pointer. This region is a trapezoid, so you can break it up into triangles if you want, or whatever. I'm just going to use the trapezoid formula. That seems the most direct to me. So I'm going to take half the height times the sum of the bases. So that would be 1/2. Now the height is the distance from one parallel side to another one, so that would be half of 2 times the sum of the bases. The bases are, let's see, one base is, looks like 1, 2, 3 and a half. So 1, 2, 3 and a half. So 3 and a half plus the second base is 2. So that is 1 times 5.5. So -5.5. Okay, so we've got this region is -5.5. And then the last green region, it's another trapezoid. You can break it up into a rectangle and a triangle. You can even count squares if you want. I'm just going to use the trapezoid formula again. So it would be 1/2, oops. It would be 1/2 the height. The height is the distance from one parallel base to another. So 1/2 of 2 times the sum of the bases. So that would be 1 plus 1.5, okay, or 2.5. Okay, so the last thing we need to do is add all this stuff together. So our negative areas total -10. So we'd have -10 plus the positive areas, 2.5 plus pi halves. We can simplify that a little bit more. -10 plus 2.5 would be -7.5 plus pi halves, and we'll just leave our answer like that. And then one quick correction, you probably noticed this when on part B, you probably noticed that the base of this rectangle, I said it was 5, it's actually 4, isn't it? So let's change that. Let's change this to 4. So our final answer would be 1/2 4 times 2. That's 2 times 2, which is 4. So sorry about that. Okay, I hope this video has been helpful. And if you have any more questions, make sure you ask me tomorrow in class.